Hi everyone, let's talk about session 6.1, Jacobi method. So systems of linear equations for which numerical solutions are needed are often very large, causing a lot of effort to compute using the Gaussian elimination. Therefore, we introduce some iterative techniques in which the elements of the coefficient matrix can be generated as needed from a simple formula. It is beneficial to use a method that does not require storing and modifying the entire coefficient matrix, as was the Gaussian elimination. So here we will introduce two iterative methods, Jacobi method and the Gauss-Seidel method. The Jacobi method is based on the transformation of the linear system Ax equals b into the system x equals cx plus d, in which the matrix C has zeros on the diagonal, and the vectors x is updated using the previous estimate for all components of x to evaluate the right-hand side of the equation. Do you still remember in chapter 2? We talk about the fixed point iterative method. So we have x equals g of x. X is a fixed point, right? And we use this fixed point formula to generate the iterative scheme. So we have xk plus 1 equals gx of k. So here the idea is similar. We are working with vectors. So we try to have an equation on the left hand side. We only have the x vector, and the right hand side, this is like a operation involving x, right? And then we can use this formula to generate an iterative scheme. So xk plus 1. So this is the estimated x values in the k plus 1 steps. That equals c apply on x of k plus this vector d. Okay, so let's look at this example. Consider the following systems of equations. Okay, and part A, find the third iterates x3 when the initial approximation is 111. Okay, part B, solve the matrix by Gaussian elimination, and then compute the error bound for the approximation using the L2 norm for vectors. Okay, let me change orange color. Okay, so first of all, how do we get the iterative scheme like x equals cx plus d? Well, very easy. Solve for x1. So solve for x1 in the first equation. Solve for x2 in the second equation. Solve for x3 in the third equation. Well, look at this. How do you solve for x1? Well, x1 is we move the x2 to the other side, it becomes positive x2. Move the x3 to the other side, become positive x3, and we have the 6. And we also need to divide by 3, right? So let's see, this is 1/3 x2 plus 1/3 x3 plus 6 over 3 is 2, right? And second equation, let's solve for x2. So x2 is then, we move the x1 to the other side, become minus x1. We move the negative x3 to the other side, become positive x3. And then we also have the minus 2 on the right. Divided by 3, well, that's the coefficient of x2, right? This is the same as minus 1/3 x1 plus 1/3 x2 minus 2/3. So far, so good, everybody. And x3 in the third equation. Now let's see. Well, that is, we move the x1 on the other side, become minus x1. When we move the 2x to the other side, become minus 2x2. And we still have the 4 there. Divided by 4, then we have minus 1 over 4. x1 minus 1/2 x2 plus 4 over 4 is 1. So far, so good, everybody. So on the left-hand side, I get x1, x2, x3. Well, that's the vector x. Okay? And on the other side, you see? Let's look at the coefficient of x1. Well, the coefficient of x1 here, no x1, so it's 0. Coefficient of x2 is 1/3. Coefficient of x3 is 1/3, right? This is the coefficient matrix. And then the constant vector, we have 2. The second equation, what are the coordinates of x1? We have minus 1/3. The coordinate of x2, we have 1/3. And then coordinate, oh, do I make a mistake? Sorry, this is not x2, this is x3. Okay, so this is 0 and this is 1/3. The last equation, oh, I forgot. The constant term is minus 2/3. And then the last equation, coefficient of x1 is minus 1/4. Coefficient of x2 is minus 1/2. Coefficient of x3 is 0. And the constant term is 1. See, now we have the form. This, we have x equals c. This is matrix c times x plus d. This is the vector d. So far, so good, everybody? So this formula can help us to generate an iterative scheme. Okay? So now we can use xk plus 1 equals c times xk plus d. So far, so good, everybody? Alright, now we can start. x0. The zeroth iteration, we assume to be 1, 1, 1. Okay, now x1 is c, what's c? 0, 1/3, 1/3, minus 1/3, 0, 1/3, minus 1/4, minus 1/2, 0, times x0, 1, 1, 1, plus d. What is d? d is 2, negative 2 over 3, 1. So far, so good, everybody. And you can plug this in your calculator. Alright, and let's see, what do we get here? So, let's find out. Okay, so this is our website of the matrix multiplication. But actually, here this website can only help us to find matrix multiplication. But using your graphing calculator is better because you can do addition, multiplication, and subtraction within the same line. So it's easier. Okay, but I don't have a visual. I mean, I don't have a. So in my screen, I cannot show you an actual calculator. So I need to borrow this website. Okay. By the way, do you realize this matrix? Do you realize this matrix C? The diagonal elements are zeros, and that's always the case because you solve x1 from equation 1, so there's no x1 on the right hand side. Okay, and then you solve x2 from equation 2, you solve x3 in equation 3. So the resulting matrix you get, the diagonal entries are just gonna be 0. Okay, let's continue. So we use, oops, this is 1/3. This is 1/3. This is minus 1/3. And this is 0. This is 1/3. This is minus 1/4. This is minus 1/2. And this is 0. B is 1, 1, 1. Okay. Okay, so this is what we get. Keep in mind, these answer, we need to add the 2 and the minus 2/3 and 1 there. So let's look at the first coordinate. First component, 2/3 plus 2. Well, 2 is like 6/3. So 2/3 plus 6/3 is 8/3. Is that okay, everybody? So we have 8/3. Next one. Minus 2/3. Oh, plus 0. That's minus 2/3. And then minus 3/4 plus 1. Oh, that's 1/4. Is that okay, everybody? Yeah, but your calculator should have the multiplication and addition, so you can do all of them together. So everybody, please learn how to use your calculator. Okay, and so that's x1. x2 is same thing. 0, 1/3, 1/3, minus 1/3, 0, 1/3, minus 1/4, minus 1/2, 0. You may ask, do you need to write all these? Yes. Please show your steps. I allow you to use graphing calculator, but you have to show all your work so then I understand, I can know that you really actually understand those materials. Okay? Alright. So let's see. Now we change our vector to be 2. Oops, not 2. 8/3. This is minus 2/3. This is 1/4. Okay, and what do we get? Minus 5/36 plus 2. Oh, so 2 times 36 is 72. 72 minus 5 is 67, right? So 67/36. Okay. Yeah, and then minus 29/36 and minus 2/3. Well, 2/3 is like 24/36. Minus 29 minus 24 is minus 53, right? 29 and 24, we get 53. So minus 53/36. Okay. So if you have your graphing calculator, you don't need to do what I'm doing, okay? So here, minus 1/3 plus 1. Oh, that's 2/3. This one is easier. Okay, I could also use a scientific calculator to help me to add those numbers, but I really don't want to press a lot of buttons, and so I'm just doing it by my mind. Okay, this is x2, and we want to find x3 with one more step. Okay, so copy down this. And 67/36 minus 53/36, 2/3, 2. Wow, this as number getting bigger. I might not able to calculate by my hand. Okay, let's see. So we change this vector be 67/36, and then minus 53/36, and then 2/3. So excuse me, and let's see. Ooh, So let's see. Okay, so 108, 2 is like 216 over 108. 216 minus 29. Let me see. 216 minus 29. So 16 minus 97, and then 10 minus 2, 8, 187. So 187 over 108. Is that okay, everybody? Yeah. And then, what's the next one? Minus 43 over 108. Okay, and we need to subtract 2/3. Okay, this one, I'm gonna use the calculator. So we know they're both negative, so we can use 43 over, oops. No. So 43 over 108, and then we can do what's 2/3. Okay, and that answer is negative 115 over 108. Because both of them are negative, so I didn't need to type the negative in my calculator. Is that okay, everybody? The last one. Not this one. The last one is, let's see. Oh, you know what? Instead of this website, I can actually use MATLAB or Octave to compute matrix. Okay. Yeah, then I don't need to do. Oh. Okay, next example, I can use Octave to calculate it because I want to show you more visually. So like this matrix, you can see actually the matrix. Okay. Well, what is that number? 13 over 48. We want to plus 1. So 1 is like 48. 48 plus 13 is 61. Okay, what is this number? Let's use 4 decimal places. Okay, so 4 decimal places. Let's see. By the way, the middle guy we know minus 1.0648. Okay, and then the top one we have 187 over 108. 1.7315. And then next 161 over 48. You might ask, do I have to do that? You don't have to. You can keep it a fraction form. I just want to evaluate this number because later on when we use MATLAB to check our work is easier to check if they're decimals. So 1.2708. So far so good, everybody? Okay, and oh yeah, exactly. So if we use Jacobi method in the MATLAB, and so this is what we type in. We type in the matrix A, the right hand side B, and the initial estimate x0. In our case, x0 is 111, and then this is the tolerance. This is the steps of the iterations, and then we will get the followings. You can see our value. Well, that match with our results. See, they're the same. So far, so good, everybody? Okay, I need to erase it because we still have part B, you know? But we don't have enough space here. Okay, so you know how to use Gaussian elimination to solve this matrix, right? But the number will be so ugly. So let's just use Octave to get this answer, and then we can find the error bound. All right. So, okay, let's input this matrix. A equals 3 minus 1 minus 1 1 3 minus 1 and 1 2 4, right? And our right hand side, b equals 6. Oh, bracket, I forgot the brackets. And remember to use semicolon because we have column vector. Okay, and then we have x equals a slash b. Oh, so the answer is 2 minus 1 and 1. So part B. So the true value for x is 2 minus 1 and 1. Okay, we need to compute the error bound. Okay, so the absolute error equals the L2 norm of x minus the estimated approximation is x3. Okay, and let's use L2 norm. So this will give us square root of 2 minus 1.7315 square plus minus 1 minus negative become plus 1.0648 square, and then 1 minus 1.2708 square. Okay, and what is that? Calculator. Square root of, and then we have 2 minus 1.7315. Okay, I pressed enter by accident. It's okay, we can continue here. And then plus, see, this guy subtract 1 is just 0.0648 square, and then plus 1 minus that is the same as 0.2708 square. Okay, so the answer is 0.3868. So far, so good, everybody. So this is the error bound. We can also use MATLAB to compute. Let's see here. The syntax. This is okay. It does not have the syntax. It's okay. Let me see here. So we have the matrix A, right? And let x0 be 1, 1, 1. Okay, then we can have let y be the Jacobi method. A, B, x0, and let's use the tolerance point 0.1, and we use 3 iterations. Oh, okay. So far, so good, and this is what we get. See, it matched with our answer. Here, it matched with our answer, and now we have x is a true value, right? Now we can use L2 norm of, let's see, we use x minus y, and then L2 norm. Okay, 0.38685. Let's see. 3868, close enough, because here we just take the 4 decimal places. We didn't use the exact value to calculate. Okay, but the answer is close enough. So far, so good, everybody. Yeah, if you use the true value, this is the actual, the more accurate value for x3. If you use this to calculate, you will get more accurate answer for the errors. Okay, so that is the Jacobi method. Next, useful theoretical results on convergence of Jacobi method. A sufficient condition for Jacobi method to converge to the solution of the systems Ax equals to b is that the matrix A is strictly diagonally dominant, i.e., if A is strictly diagonally dominant, then Jacobi iterations converges. Wow, do you remember in chapter 3, we talk about strictly diagonally dominant and symmetric positive definites, SDD and SPD, right? So strictly diagonally dominant means the diagonal elements, the absolute value. So in each row, the absolute value of the diagonal elements is greater than the sum of the absolute values of the other entries in that row. Okay, a necessary and sufficient condition for the convergence of Jacobi method is that the magnitude of the largest eigenvalue of the iterations matrix be less than 1. Okay, so the magnitude, if the magnitude of all eigenvalues of the iterations matrix C be less than 1, even only if the Jacobi iterations converges. Okay, but usually we don't really check that because to find an eigenvalues for a matrix takes more work than using the Jacobi method. So far, so good, everybody. Okay, session 6.2, Gauss Seidel method. The Gauss-Seidel method is similar to Jacobi method. It also transformed the linear system into a system x equals cx plus d. So actually, this is the same system, okay, in which the matrix C has zeros on the diagonals. However, in contrast to the Jacobi method, each component of the vector x on the right-hand side of the transformed equation is updated immediately as each iteration processes. So let's look at the following example. Consider the following linear system of equations, right? So here we have the same equation as before. Okay, and part A, we want to find the third iterates when the initial approximate is x0 equals 1, 1, 1. Okay, so now let's recall. How do we, let me change that to, how about let me use purple color. Okay, so to find the C and D, same way as before. Solve for x1 in equation 1. Then we have x1 equals minus 1/3 x2 minus 1/3. Oh, sorry, it's plus, right? Because we move to the other side, it becomes plus. X3, and then we plus 6/3 is 2. So far, so good, everybody. Okay, and x2 is, well, we solve for x2 from equation 2. Move the x1 to the other side, be divided by 3. We get minus 1/3 x1. And then we have plus 1/3 x2. And then we have minus 2/3. So far, so good. x3, well, x3 is move the x1 to the other side, become minus x1, and we divide it by 4. Move the x2 to the other side, and 2/4 is the same as 1/2. And 4/4 is 1. So far, so good, everybody? Okay. Do you still remember the Jacobi method? We then write this in terms of matrix C and constant vector D. But for the Gauss-Seidel method, we don't do that. And what do? Is we put some index on it. Okay, so what are the index? Let me use a different color. So the new vector x1, the first component of our new vector, is 1/3 x2. So the second component of the old vector plus 1/3 the third component of the old vector plus 2. And x2 of the new vector is minus 1/3 x1. Because we already get x1 of the new vector, so here we use the x1 of the new vector. We don't use the x1 of the old vector. And x2, we don't know it yet, so we use the old vector. So you see, we update it immediately. Okay, within a step. x3 new, x1, we already know x1, so update it. x2, we already know it, so update it. So far, so good, everybody? Okay, so this is how we calculate. Alright, let's continue. So you don't use matrix to calculate, you just like do the regular calculation. So first step, x0 is 1, 1, 1. Well then, x1, 1. Okay, so this index denotes the estimated vector in the first step, and this index is the coordinates of the vector. Is that okay, everybody? Okay, so this is 1/3. x2 old is 1 plus 1/3 x3 old is also 1 plus 2. So 1/3 plus 1/3 is 2/3 plus 2. So 2/3 plus 6/3, 8/3. Right? And then x2 of the first vector is minus 1/3. x1 new is this new guy. Put it here. 8/3. Plus 1/3. x2 old is 1. Minus 2/3. Yeah, so the Gauss-Seidel method is harder than the Jacobi method because there are more data and you have to update it in each step. So you have to be very, very careful, and you have to figure out which number you choose. Okay. Let's see. This is minus 8/9. This is plus 1/3 minus 1/3 is the same as minus 1/3, right? And 1/3 is like 3/9. 8 and 3/9 is 11/9. So far, so good. x3 coordinates minus 1/4. x1 new is 8/3 minus 1/2. x2 new is negative 11/9, right? And this put it here, and then plus 1. Okay, what is that? Okay, let's use calculator. Okay, calculator, we need your help. So here 8 and 4 cancel, so we get minus 2/3. Minus become plus. 11/2 times 9 is 18. Okay, you see? I need to go up here. Okay, and then plus 1. So sometimes if you can do some calculation in your mind, then you don't need to type so many things in your calculator. So what is that number? 17/18. So this is x1. x1 is 8/3 minus 11/9, 17/18. Okay, now let's calculate x2. x2 first coordinates is 1/3 of x2 old, which is minus 11/9, plus 1/3 x3 old, which is 17/18, plus 2. Okay, calculator, we need you. So we have negative 11/27, and then plus 17 over 3 and times 18 there. Oops. Okay, plus 2. And what is that fraction? 103 over 54. Okay, x2 of 2, that is minus 1/3 x1 new. x1 new is 103 over 54 plus 1/3 x2 old, which is minus 11 over 9 minus 2/3. Okay. Yeah, so a lot of calculation in our course. We're dealing with a lot of numbers and we have to be very, very careful. So 3 times 54. So if we pick the wrong number, or if we plug in one wrong number, the whatever falls is gonna be all wrong. So we have to be patient and calm down, do it slowly. Okay, so what is this number? 277 over, let me see. Oh, you know what? Here I have a mistake. This is x3. Okay, so x3. So this is wrong. 17 over 18. Our answer in the first step is still good because x1, x2, x3, they're all 1. Okay, but here we see sometimes we make a mistake. Then luckily we'll figure it out here. Yes, so we actually need to do it slowly. So this should be 17 over 3 times 18. Okay. And this is plus. Let's see. It's plus. Oh, you see? Here, this is 18. I pressed A, but sometimes my button doesn't show up here. Oh, so the answer is minus 80 over 81. Okay, so that's x2. Luckily, we only need to do like to find x2. We don't need to do 3 iterations. Okay, so minus 1 over 4 x1 is 103 over 54. Minus 1/2 x2 is negative, and positive. 80 over 81 plus 1. So that equals minus 103 divided by 4 times 54 and plus 80 over 2 is 40. 40 over 81 and then plus 1. So what is that answer? So the answer is 659 over 648. Okay, so our x2 is 103 over 54 minus 80 over 81 and 659 over 648. Okay, so far so good, everybody. And let's see, what are these approximately to? Because then we can use Gauss shadow method to check our work. And let's copy down here. this number is 1.01697. We round up, becomes 1.0170. Okay, so 1.0170. And then the negative 80 over 81, 0.987, round up 7. Okay, so 9877. And then the first one, we have 103 over 54, 1.9074. So far, so good, everybody? Okay, now let's see. So this is how we use the Gauss shadow method. Okay, and we can also compute the error bounds using the L2 norm. So, you remember the results we got from last time? We have our true value was 2 minus 1, 1, right? Then here, x minus x2 using L2 norm. Square root of 2 minus 1.9074 square plus minus 1 minus negative become plus 0.9877 square. And then 1 minus 1.0170 square. And what is that answer? Let's see. So that answer equals, let me just copy this down. I don't need to type the whole thing again. 2 minus 1.9074 and so 1 minus that. Okay, we don't know what this is. So and here we change to parentheses 1 minus, 1 minus that number or that number minus 1 is the same thing because it is squared, so it's the same. 9877. And then last one, 1 minus that, so it is 0.017. Okay, so you see this norm is much smaller than the previous steps, right? The previous methods, Jacobi method. 0.09495. 0.09495. Okay, our last example, we have the norm is 0.3868. See? Now we have 0.09495. Let me show you the MATLAB how to compute. So the syntax is shadow. Okay, let's see here. So we can go up there, and instead of Jacobi, I can delete Jacobi and just replace by shadow method. Okay, so 2.0, and we want to use 2 steps. Okay, we didn't calculate 3 steps, 2 steps. 1.90741, yep, and minus 9876, okay, yeah, that match. Last one, 1.0170, and that match. Okay, and let's find the norm. 0.09495. Yeah, it match. So you can see, in general, the Gauss shadow method converge faster than the Jacobi method. Okay, so here is the convergence of the Gauss shadow method. If the matrix A is real and symmetric with positive diagonal elements, then the Gauss shadow method converges if and only if all the eigenvalues of A are real and positive. Well, if you can remember, that that is one of the equivalents to say A is symmetric positive definite. So that's why we say if A is symmetric positive definite, then the Gauss-Seidel method iteration converges for any initial vector. Okay? And also, if the iterations matrix C is non-negative, then the Jacobi and Gauss-Seidel methods either both converge or both diverge. When they both converge, the Gauss-Seidel method converge more rapidly. Okay? So if A is strictly diagonally dominant, the Gauss-Seidel iterations converges. So now we have if A is strictly diagonally dominant, then both the Jacobi method and the Gauss-Seidel method will converge. So keep these in mind because I might ask you true or false questions. Okay. So far, so good, everybody? Yeah, so if A is strictly diagonally dominant, the Gauss-Seidel methods converge. Okay, and if A is symmetric positive definite, the Gauss-Seidel method also converge. Okay, that's so important. And for the Jacobi method, this is also, see, if A is strictly diagonally dominant, Jacobi method converge. So those are the important concepts. So far, so good, everybody? Okay, so we will continue in video parts B. See you soon. Bye.